Lately, there has been much talk about post quantum cryptography or PQC. In this Keep It Safe, Secure series, we will talk about PQC. What is PQC? Why do we need PQC? When is PQC required? And also questions such as how do we prepare for PQC? What are the challenges with PQC? Is PQC a quantum technology? Now, before we get further into understanding PQC, let's take a look at what is cryptography and how cryptography is different from security. Cryptography is a set of techniques or algorithms which keep the data secure. Cryptographic techniques are based on mathematics, information theory, and sometimes physics too. Whereas security is a combination of cryptographic techniques and human factors to keep the information secure. Data becomes information when it is analyzed and understood. Now, here is a timeline to understand why PQC is so called, and let's walk through this. Now, the cryptography that we use today is referred to as classical cryptography, sometimes as legacy cryptography too. Certain aspects of classical cryptography introduced in 1970s are the backbone to today's information security. And that includes today's internet security, network security, application security, and everything else that we use today. This classical cryptography relies on the computational difficulty of solving specific mathematical problems. The computers and supercomputers that we use today are unable to solve these mathematical problems in meaningful time. The classical cryptography rides on this computational complexity. Until 1994, we thought these cryptographic techniques are invincible. But then in 1994, a mathematician by the name Peter Shor published a mathematical proof of a threat that would make the classical cryptography vulnerable. This published proof is basically a quantum computing algorithm and is referred to as Shor's algorithm. In 1994, there was no quantum computer, and so this Shor's algorithm perplexed the cryptographic community, though the algorithm itself was a major boost to the topic of quantum computing. In 1998, the first 2-qubit quantum computer was built. And then starting 2001, the first toy implementation of Shor's algorithm was demonstrated. It is considered a toy implementation because the quantum computer that was used was error prone and it cannot work with large numbers. Very large numbers are used in today's cryptography. So the cryptographic community was perturbed and the question still was whether quantum computing advancement will continue. Will it continue to evolve into a quantum computer with sufficient improvements in its error corrections so that it can be used to break classical cryptography? And that remained the question in the early 2000s. So, as the advancement in quantum computer continued and cryptographically relevant quantum computers became a reality, the cryptographic community coined the term post quantum cryptography in 2006. And the purpose of the PQC was to research and explore cryptographic techniques, mathematical constructs which will not be vulnerable to quantum computing. That is, the yet to be proposed cryptographic techniques will resist quantum computing based attacks. Hence, these PQC algorithms rely on the computational complexity of solving specific mathematical problems that are difficult for quantum computers as well as computers and supercomputers that we use today. Hence, the proposed cryptographic techniques are called post quantum cryptography or PQC. The community soon realized that moving away from classical cryptography to PQC is not a trivial task. NIST, an agency in US Department of Commerce, has shepherded advances in cryptography in the past, AES being a good example. In 2016, NIST starts a formal process to develop PQC algorithms. This triggers further activities to research and develop the transitions which will allow the migration from classical cryptography to post quantum cryptography. The PQC migration to a new cyber security infrastructure will consist of several transitions. Today, the quantum computing is advancing at a doubly exponential growth rate, a pace of growth rate we've never seen before in modern technologies. And add to that the advances in heterogeneous computing, such as those that avoid the von Neumann bottlenecks. The threat to classical cryptography is real. Harvest now decrypt later attacks pose a security concern as organizations consider implications of quantum computing. And the risk of harvest now decrypt later is real. So the question now is, when will classical cryptography as implemented today is compromised and thus be rendered obsolete? And that's few years away, maybe a decade or so. But the challenge is migrating to PQC. We want to migrate all our systems that use classical cryptography. And that classical cryptography has to be replaced with PQC. And all this has to happen with no disruption to our daily operations and business activities. And it's not a trivial task. So the immediate driver to migration is to remove the risk of handle attack. The transitions to PQC migration is critical and urgent. Now, the pace of growth of research and technology to decimate classical cryptography is accelerating. So, migrating to PQC, it's a global effort spanning all countries, institutions, and enterprises. A global effort to standardize, develop, and implement post quantum cryptography has started today, is in effect today. And this effort is two pronged. So, the first is the one led by the NIST driven process to standardize the PQC algorithms. And the second is a framework for PQC migration. The framework that's being put together by the industry leaders, the academia, consortiums, and regulatory agencies. And this is to help us get prepared to be ready with PQC to avoid the risk of handle, and so that eventually, when the classical cryptography is broken, only PQC and other quantum resilient, quantum safe technologies, when deployed, will keep our data safe and secure.